Hello guys, let's solve today's GFG POTD array to BST. Given a sorted array, convert it to height balanced binary search tree. Return the root of the BST. Height balanced BST means a binary tree in which the depth of the left subtree and the right subtree of every node never differ by more than 1. The driver code will check the BST. If it is a height balanced BST, the output will be true, otherwise the output will be false. Okay, so let's solve it, guys. Basically what he is saying is, see, let's understand what's a binary search tree first. Binary search tree means suppose any tree is there, suppose assume 3, 0, 2 and 3 here. BST means the node value should be less than the left node value, and this node value greater than this left node value and less than the right node value. This is one condition, and this condition should be satisfied by these nodes, left nodes and also right nodes. Okay, so means basically 2 it should be greater than left and less than right. So the same condition holds for every node here. So that's what a BST is. And he's saying height balanced BST. Height balanced means the difference between any two nodes should not be 1. Okay, means should not be greater than 1. Okay, should not be greater than 1. That's it. Maximum is 1 or 0. Okay, so we'll solve it, guys. See, what they told is here is a sorted order. Should no recursion, guys, to do this. Okay, so this is a sorted order, right? So obviously this is a sorted order. Now we have to arrange this in a BST with height balanced. So we'll think a logic to put the values in BST height balanced, right? So obviously I'll write normal height balanced code, normal height, not code, tree 1 2 3 4 5 6 7. Now is this height balanced or not? Obviously no, right? Because here height is means here this node and this node height is differing, right? So that's why this is not a height balanced. Here you have to, what we have to understand is, after completing a single level only you should go to other level. Okay, see, otherwise suppose here I didn't finish this level and I went to this level, so the height difference changes, right? So after completing a single level completely you should go to the other level, otherwise we will not go. Okay, so that's the logic. Now what I will do is, see, I think you know on binary search, basically binary search. So if you don't know, no problem, you can watch this. I'll take this as low element, and or I'll take left and right. Yeah, that's more better. This is the left element and this is the right element. This is 4 here. Now consider 3 elements are there, 1 2 3. You have to arrange this in a BST with height balance. It means how will arrange 2 1 3, right? Obviously 2 1 3, because 2 will be the middle element, because 2 should be greater than this one and less than this one, right? So 2 will be the maximum node, right? The same case goes here. Here left element is 1, right element is 7. No matter how you look, 4 will be the middle element, right? 4 will be the root node element, so obviously 4 will be the root node element, right? Okay, but how can we get what are the left and what are the left? The values which are less than 4 obviously should be less than, means in the left side, right? Means the values, these 3 are less than 4, so they should be obviously in the left, and this is greater than, they should be obviously in the right, right? If we didn't take the middle element, the value changes, right? If we take this element, these are 4, this is 2, unbalanced, right? So means height changes if you take it properly. So middle element should be 4. Now here what we are doing, we are checking for left and right, right? Now in the search space, now these 3 values should be here, these 3 values should be here, right? Now what I will do is, I'll move this pointer to here, means 4 is completed, right? I'll mark 4. Okay, I'll mark 4. Now remaining are 1 2 3 and 5 6 7. So if this is the middle element, obviously these left node values will be 1 2 3, right? Now in this, now again search in this space. Okay, for again searching, this is the left, again this is the middle element, right? Now let R, means in this search space, L1 R1. Okay, now again in the search space, same function, right? You have to arrange this in a BST. I told you, right? If this should be a BST, this should be a BST, this should be BST. Left rail should be BST height balanced. Height balanced means middle element should be again root node, right? So again in this root node is 2, left 1, right 3, obviously. Or we can say, so middle element is 2, obviously. and we are moving this right, means in this search space. Now consider this search space, okay, this one left. I'll tell about right node, but left node 1 comma 2 comma 3 in the search space. Here left is there, here right is there, middle element is completed, right? 2 we wrote. Now in this in this in this 2, this left part will be left side of 2, in the right part will be right side of 2, right? So left part, what is there? 1 is there. Again we'll write left and right, right? So same element left and right. So again we'll do, again 1 will come here, right? And the right part 3, right? Obviously 3. So the right part will go here. So now 1 is completed, 2 is completed, 3 is completed. We'll put the right part. So like that, again we'll discuss the right part. In this right part, what 5 comma 6 comma 7, we'll run the same call again, same function call. So now here 5 is the left part, 7 is the right part. Now to arrange this in a BST, 6 should be the node, right? Obviously. So 6 will be the node. So we'll push 6 here. Again we'll go to the left search space. Means left should be a BST, right should be a BST. So here, yeah. So left will be 5. So again for 5 is left and 5 is also right. So 5 will be here, 7 will be here. So that's it, guys. That's the logic. What we'll do is normal, what we can say, normal we'll do, but first we'll check the left side and then go to right side. Okay. So that's it. Yeah. So let's go into this. Easy code. You should know recursion, guys. English. Converts sorted into BST. Okay. Vector int nums. Okay. Next int left and int right. Okay. Int mid value means that should be the middle element, right? So that's why I'm calculating it. Left plus right by 2. Okay. And if see, now you can ask me, here 1, here this, suppose here 1 is there. Now left and right. Now what will happen is, again mid will, what it will do, mid will write left plus r by 2, right? So 1 plus 1 by 2 it will do. So 1 plus 1 by 2 is again 1. So when it goes out of bounds, means sorry, left greater than r, means it is possible, but in some case left greater than, see here left is there, if here is left is there, here right is there. So they are moving towards here, right? Here mid is there. First what we will do, first r will go here. So they are moving towards, when they cross each other, it's not possible, right? Obviously left should not be less than right, because it is in a sorted order, right? It's in a sorted order. It's a polarization concept. Left should be less than right. Low should be less than high. In a BST here also, left should be less than right. If anywhere this happens, this should return null road, right? Return null. Means in any array, left value should not be less than right value, right? Means suppose nothing is there, then only that happens. So okay, next I'll create a new node. Node star root. Okay, new node star, new node. Okay, with value nums. Okay, nums of mid. Yeah, obviously this will be the mid. Okay, so now what we'll do is, we have to calculate the left part, right? So root of left. Now what will be root of left? The root of left will be, but see, same thing, root of left will be this search space, right? So with values what, L1 R1, right? So that's only we'll do. We'll function same vector nums, but what we'll say, search space, right? Initially this long is a search space. Once we completed this one, we are moving to this search space, right? So L remains constant, R remains mid minus 1, right? So that's the answer. Yeah, mid minus 1 and root of right. Okay, same thing, function nums, upper one also nums. Yeah, here left and mid minus 1, here mid plus 1 and right. See, after completing the left, after completing this nodes, we'll go to here, right? So here what we will do, this will be the search space. 4 is over, left node is completely over, remaining is these 3, right? 5 6 7. So search space will be end only, but mid means L should move on, right? L should be mid plus 1. Same thing as first we are doing for this none, and we are reducing search space for this and this, like that. Okay, So mid and r plus 1 here. Return root. Okay, I hope it works fine. Function nums initially search space 0 to l minus 1, right? Length, okay, nums dot size minus 1. Yeah, I hope it works fine. Yeah, let me submit it, guys. It's easy one, not that hard, but the logic is important.